So first, let's finish the last two slides from the small signal stability section. We didn't finish due to some technical issues last week. So this slide summarizes the method to place controllers for damping controls to improve small signal stability. We have talked about the mode shape, mode composition. The mode shape will be defined by the right eigenvector of the modal matrix. Mode compositions are defined by the matrix made by the left eigenvectors. So we also can utilize the mode shape matrix phi to find which state variables have the best observabilities of the mode, and use the matrix made by the mode composition to find out where to place those controllers. So which variables will have the largest contribution to the mode. So we can utilize the matrix phi and the matrix psi to find out the control variables and also the variable to collect the measurement data to observe the state variable. So this is what we talked about at the end of the last lecture. So when you design the control input and also the measurements, which are the output, to have the best performance of your controller, it's better to place the sensors at the location where you have the largest the mode observability. Mode observability will be depending on the mode shape matrix. And then when you place controller, it's better to have the largest mode controllability. That depends on the psi matrix, which is about the mode composition. Assume you can have like just single input control for the control, which is receive the negative feedback from a measurement data data y. So data u here should be the location which had the largest mode controllability, and data y will be the location you have the largest mode observability. If you cannot achieve the best mode of controllability observability, so you need to find a location which are not too bad, such as you can design the feedback control loop, and to make the final after control, the mode will have the expected frequency and damping. So you can design the frequency or damping here by designing the feedback control block. So the last slide of a small signal stability just implement this idea for controlling the damping of the two-area system. This system is going to be utilized for the project. We also use the same system to do a number of tasks. So for this system, if there's any fault at this location near bus number 9, a short circuit, then the line can be tripped. So based on the data on this is the rotary angle of the first generator, you see a swing has swings, 2 swings, then the system just become unstable. This generator just go out of step. This is not a very typical transient instability. It's more like the bad small signal stability, and you have growing oscillation, and then finally growing oscillation will develop to the transient instability. So which means if we can add any damping control before the out of step happens, we may be able to stabilize the system. So here we don't have to design the transient stability controller. We can use just a damping control method to improve the damping. Then we can stabilize the system. So here we're going to use SVC. SVC is originally placed for supporting the voltage and to provide dynamic reactive power. But because it can support voltage, it can mitigate the voltage variation at any point. Remembering for the system involved in the interior oscillation at the center of oscillation, which is the middle point, typically the middle point of the two ends, which is around maybe bus A, that one will have largest angle voltage deviation. Okay, so if you place SVC there to reduce the voltage deviation, you also improve damping of the system. So definitely we can put the SVC on bus 8, which will be the input to the system. And if you want to do the mode controllability study, you'll figure out this bus also has very good mode controllability. And another index mentioned by the textbook is called bus participation factor. We can talk about this factor a little bit more in the voltage stability section, but definitely this one is also related to the mode controllability. So basically this location is not that. So we just put SVC there. And if we want to collect some data, we need to find location with good mode observability. So from the study on the textbook, so the line current between bus 9 and bus 10 will be the measurement with good mode observability, which means if the system really oscillates, by collecting the data of the current between bus 9 and 10, you can see the oscillation clearly, so it has good observability. So we can collect data from that current and give the data to the SVC as input signal. Definitely we can design the feedback control system and which can change the eigenvalue for this oscillation mode to any frequency or damping we desire. Okay, so the blue one will be the input, which is SVC to control the voltage deviation. The red one will be the current, which will be the data collected from that line current. So this GS will be approximate or equivalent transfer function to describe how the voltage deviation can influence the line current. So this will be our transfer function of the system. Next, we're going to design the feedback control. Okay, so GS will be the original system, HS will be the feedback control. So it will form a negative feedback loop, and then we can design the dominant eigenvalue for that control loop. For instance, if this is our desired eigenvalue, this is not what's already happening on the system. It's just our target. So this one we will have this oscillation frequency and also this damping ratio. Okay, this damping ratio means 16%, which is very high, which much higher than the original. Original will have damping ratio negative, right? Based on the waveform. So this board diagram just shows the approximate transfer function from the voltage input to the current output. So this peak actually corresponds to the inter-area frequency, because inter-area frequency is around 0.5 hertz, right? So we want to design the edge, the feedback, and to make sure the closed loop function will have the eigenvalue as we design at lambda 0. So from previous slides, if we know the JS, we know the transfer function, we only just need to utilize this formula. So this one tells us to design the edge, we need to make sure when we plug in the design eigenvalue to the feedback, and it need to generate this gain and also this phase shift. Okay, that will be the H value for this frequency, for this eigenvalue. But for any other frequency, it can have other eigenvalue. But our target is not to change everything about JS. We only just want to design the lambda near that inter-area oscillation. So this will be the control design. It's very similar to the PSS, power system stabilizer. Just introduce some phase lead, phase lag compensation, and to give us that function. So if you draw this, because everything is given. So if you use MATLAB function to draw the board diagram, you will see the board diagram will compensate the board diagram of GS, and finally will give you the the desired, the amplitude, the gain, and also the phase shift. So if you implement this design, you see the damping will be largely improved. So there's the two curves. The solid line will be the SVC without supplementary control, which means you don't do the remote control. You only just place SVC there. Using the local data, you just try to mitigate the voltage deviation. So you can make the waveform be decaying, not growing. So the damping will become positive. But if you apply the supplementary control by utilizing this feedback, it will give you much bigger damping, right? The waveform will be decaying much faster. Okay. So in this table, it gives you the frequency and damping ratios with or without the control. If there's no control, the damping ratio after the fault, it will be negative. Okay. And if you place SVC but without connecting to that remote signal, the damping ratio will be positive. But this one is around 1.5%. It's still lower than typical 3 to 5% of the industry criteria, the threshold. And if you do the remote control, so this one will become 16%, which is much bigger than the threshold. That is the same as what we designed. Okay. So this is very brave, just introduction about the idea to design this damping control utilizing the mode shape and mode composition. So please read that section in Quinter's book. So there's more details. Okay, so now we need to move to our new session of transient stability. Let's switch. Okay, we'll move to the next section, transient stability. Okay. All right, so by this session, we're going to cover two approaches to study the transient stability. The first one is the time domain transient stability simulation. So by this part, we're going to introduce the two types of integration methods to solve the dynamic model of a power system, including explicit or implicit methods. Then we'll talk about how to simulate a general power system with multiple generators. Next, we'll also talk about some direct method. So by using this direct method, and you can judge the transient stability based on, for instance, some equal error criterion for a single machine infinity bar system, or for using some energy function for multi-machine system. So when we concern transient stability of a power system, we want to make sure all the generators operate in a synchronous way, which means their frequencies are pretty close, around 60 Hertz, even subjected to some large disturbance. Because we learned the small signal stability, so the large system may have many oscillation modes. There may be a local mode, interior modes. So for the interior modes, you will be able to see a group of generators oscillating against another group of maybe rest of system. So it's totally fine if you see coherent groups of generators some generators tend to become maybe closer to each other, but some will have a different phase. As long as over time the generators stay together closely around the same frequency, we still consider the conditions as a stable condition in terms of transient stability. So the synchronism will be the critical for any power system to maintain transient stability. So even this after a severe disturbance, the severe disturbance can be any outage of a transmission line, generators, or maybe disconnection of a large load. So this is one case when the system loses transient stability. So you see one generator, it becomes just out of step. So this one generator, the first figure just indicates me this generator. So if you have some disturbance near that group, and that can make that power plant flying away, right? But the remaining system, even if form another two coherent group, but they still stay pretty close. So the rest of system is still stable, but this generator will be tripped. So this is one scenario of a single generator losing transient stability. Another case is more severe. So if you have maybe disturbance near the black region, so that will make multiple generators in that region going out of step. And the remaining system, even they may form several groups, but they will stay together. Okay, the second scenario will be more severe compared to the first one. Because for the first one, you can definitely just trip that generator. The rest system will be fine. You can depend on the balance of load. You want to decide whether you want to reject some generation or trip some load to maintain the rest of the system to operate at 60 Hertz. But for second scenario, you may not be able to trip everything in that group. You may have to, if you cannot save the system by load shedding, you may have to do maybe islanding, right? You have to form an island for that out of set the group of generators to operate on their own. That is more critical condition. Compared to small signal stability, so here we're more interested in severe contingencies, so severe disturbances. So you may expect to see a large variation of angle, frequency, flow, voltage, magnitude in most of the area if transient instability scenarios really happen. So we definitely need to model and study the nonlinear characteristic of the system. We cannot utilize any linear model to study transient stability. If the system is a synchronous, maintain all the generator operate in synchronism, and the angle separation between any two generator need to be maintained within a set limit. So usually that angle will be much lower than 180 degrees, right? Because based on the power angle curve from the single machine infinity bus system. So if this is angle, this is P, this is just model the single machine versus the infinity bus. So then the single machine angle separation from the infinity bus usually is less than 180 degrees. So initial angle can be very small. If the angle has large swing, it should not reach 180 degrees. So that, although it's from a single machine infinity bus system, but can be applied to even multi-machine systems. So any two generator need to maintain a small enough angle separation. If transient stability really happen, that can be evident very quickly within just 2 to 3 seconds. Just use those two scenarios as one example. So if you draw two lines, which is envelope of 180 degrees, so you can see the angle separation, the largest angle separation between maybe the blue curve and one of the green curve will separate, will reach 180 degrees quickly, just in 1 or 2 seconds. So which means you need to take control action as soon as possible. There's not much time for operators to react to what happened. Everything has to be designed offline. If you want to utilize an adaptive controller, that adaptive controller has to be very quick, very fast. If you want to do some online calculation, it has to be extremely fast. So there are two approaches for transient stability analysis. Both approaches need to handle the model of the power system. So for the model, which will include the ordinary differential equation and algebra equation. The ordinary equation will be describing how the state vector will change over time based on the rate of change defined by the vector field of the equation. And the algebra equation includes everything else, focusing on the variables which are not state variable, like voltage, current, so which are typically not considered state variable in transient stability analysis. We can call the whole set of equation as DAE, or that differential algebra equation. So there are two approaches. The first one is just a direct approach. The second is indirect approach. For direct approach or direct methods, so they can assess stability without solving the DAE model. Okay, so such methods, they don't need to solve the DAE, but they can tell you the system is stable or not stable. How can it do it? It just utilize some methods from Lyapunov second method for stability based on this theory. For instance, you can define an energy function or transient energy function, which is either an accurate or approximate Lyapunov function. So we'll talk about Lyapunov function later. Then you can compare this energy to some critical value, the threshold value. If it's higher than the threshold, which means it will escape from the stability region or domain of traction. If it's lower than threshold, it will stay within that domain. Okay, the system will be stable. Indirect methods, typically the time domain simulations. We need to solve an initial value problem for the set of DAEs, starting from any initial state at a certain time. Basically, you need to utilize numerical method to solve the DAEs for the system response at any desired time. The simulation need to be done for a long enough period until you clearly tell the system to be stable or unstable. Okay, so if you see most of variable, they have very clear trend going back to the equilibrium or static condition, means the system is stable. If there's any variable is flying away, you can stop there. You can give a judgment of a transient instability. Okay, let's talk about the numerical integration method. For transient stability analysis, let's consider solving the nonlinear ODE first. Later, we'll talk about how to solve the algebra equation. So such numerical integration methods are designed not for just for power system, is for simulating any nonlinear system. Assume we want to solve the state vector ST, and at the time step h can be a very small time step. For power system, usually that one can be a millisecond for transient stability simulation. And we need to know initial condition. Okay, so how to solve this equation? So one idea is if the solution of the state vector as a function of time can be approximated by a Taylor series expansion. So this is solution, which is a function of time, and it can be expanded by this series. We'll have the initial state, we have a first order approximation, second order approximation. That's basically just Taylor series. Okay. So the first item will be initial state, and the second item, it depends on the rate of change or the first order derivative of the state vector. which is exactly just the regional nonlinear function f by plugging the initial state, initial time. Okay. And then if we continue, there will be a second order term. Definitely you want to continue, you can have a third order, fourth order. Okay, so the ice-spacing method is just take a number of items from this Taylor expansion and as approximation of the final solution. So you can do that approximation for each time step, which means if you have a finish, maybe time step k, number k, you have the state vector value and time at the end of this step. Then utilize that state vector value as the initial point. You plug in that Taylor series and to predict the next value of the state vector. But as ice-spacing method, it's going to compute the future value of the x using only the value from a previous time step, which means you can just go straight forward or using the old value to calculate the future value, then the future values will become old value and continue this process. Example would be that's a forward Euler method or Runge-Kutta method. So here is one example of such method. So if you already know the value at k step, sk, okay, so you only take the first two terms from that Taylor expansion. And the first item will be the value at the end of previous step. And then you calculate the f value, also utilizing the x and p from previous step. So this one will give you the first order derivative and multiply by the time step. So this one will give you a linear approximation about your future state. Okay, so this is just the forward Euler method. That is the simplest numerical method you can have. It only utilizes first two terms of the Taylor series up to the just first order derivative. So that's why this method is called first order method. As first order method, it ignores any second order term. So the accuracy or truncation error will be around second order. So depending on the size of h, the interval. So if the h is smaller, the error can be smaller, but it will change as a quadratic function of h. Just give you some visual example on how the forward Euler method solve a nonlinear function. We consider that single dimensional example. So here it does a single variable. Assume this black curve will be that nonlinear function f. So that describes how the first order derivative of x will change nonlinearly over time. And h here is just a time interval. So we are going to solve this function for each interval of h. So which means if we know exactly the initial state at t0, we're going to solve the value for t1 and then for the t2. And here, this dot actually clearly tell that is actually the accurate value. So if we're able to simulate at 100% accuracy, we need to hit that point. So that will be as t1, all right? And you can draw a line. That is a straight green line, just indicate how the initial state will change to that the new state. So that green line will have the slope, which is our target to predict. So we are going to utilize this Taylor expansion, only use the first order derivative to predict that slope. For forward Euler method, the slope is actually predicted at the beginning point. So which means we draw a tangent line just at the starting point. We draw this red line. And we use this red line to predict that green line. Okay, so at t1, so this will be our estimation of the accurate value. So you can tell there's a gap between the red dot and also the circle on top. Definitely, if you make h be very small, eventually this tangent line will be closer to the true curve. But if you stay with this time step, and for next step, you're going to utilize the value here to draw another tangent line. You get the second one. If you continue this process, eventually you will have piecewise linear lines, right, to approximate that curve. If the time interval is very small, that piecewise linear curve will be very close to the accurate curve. But if H is large, finally the simulation can diverge from the true solution. This is called the first Euler method, forward Euler method as first order method. Another type of methods are called implicit methods. Implicit method different from the explicit method, so they can utilize future time step to give you better estimation about that slope. Examples such as backward Euler or trapezoidal rule method. So for backward Euler method, it is called a Euler method because it's another first order method. But if you compare those two, the key difference is in the forward Euler method, everything on right-hand side of equations are already known. So they take value from previous step. But for backward Euler method, so you need to plug in a future value. This is exactly what you want to compute. So you may ask, how do I know that value? Okay, in order to compute this state vector value, I need to assume I already know it. Then plug into the F to give me a slope, then I can calculate that. So this is just the formulation of this method. But how to solve this equation, it will be similar to solving like power flow equation. So you have n nodes on both sides. You have to do some iteration. So the answer is you cannot calculate this equation just by one time calculation with the forward Euler method. You have to give this one some initial guess, then calculate this one, and you plug in back. So you have to go through some iteration until the sk plus 1 on both sides will have pretty close value. Then you can stop there. So even the formula look as simple as the forward Euler method, but computation can be more complex. So if we use that figure to illustrate how this method approximate that curve, so it will at the T1, instead of using the slope at the beginning point, it's going to utilize the slope at ending point. So if I use different color. Okay, so for backward, I mean, better just use the green. For backward Euler method, it's going to draw this line because they're going to take the tangent line at ending point. So they're going to draw this line and to give you this solution. So next one, it will maybe this one. Then okay. All right. So that's backward Euler method simulation. Okay. From this example, you may feel okay. So it doesn't give you the accurate solution, and compared to forward Euler method, it's not obviously better, right? It just gives you a faster divergence of the curve, and the forward Euler method gives you slower divergence of the curve. But depending on the stability of system, if the system is stable, the backward Euler method will be much better than forward Euler method. So I'll explain that one later. Okay, next will be another two popular explicit method. So I use a blue color to indicate those methods fall into the explicit type of methods. For modified Euler method, the idea is to average two slopes estimated at the beginning and ending point of each interval, such as you can have better estimation about that slope of the green slope K. So what it does is it first draw a tangent line at the starting point. Okay, so this is same as the forward Euler method. So if you're using forward Euler method, you can stop here. Just use this point to estimate the true solution. But for modified Euler method, it asks you to do a further step. So once you know this point, you plug in the value of this point into this nonlinear function, and to get the second slope. The second slope, you plug in the calculation from the first step, and also use the time at the second step to give you a new tangent. So this new tangent is approximation of the tangent line at ending point. It may not be exactly the same, okay? But from this example, we know the K1 is smaller than the accurate slope K, and K2 is bigger than the accurate K. So if I do an average, I should get something much better, okay? So this is the average. Then I use this right line as a tangent to predict the ending point. So now this right dot will be the calculated state at the end of the first time interval. Okay. So this one is get closer to the true solution. I'm going to talk about trapezoidal. Okay, then you will be able to answer this question. Okay, if I document what formulas or the algorithm are going to implement this method, first I calculate K1, which is the same as I did for the forward Euler method. And instead of using the K1 directly estimate the state, I make the estimated state plug in back to the formula again to calculate the K2. Then at this step, I take the average of K1 and K2, okay? All right, so what is the order of this method? It's called the modified Euler method. Euler method or forward Euler method is first order method because basically utilize the first order derivative to approximate the curve, right? But here I involve a 2 or 3 slope. I have the slope at the beginning, I have the slope at the ending point, and also I calculate the average. So what is the order of this method? So this is second order method. Why is second order? Because this equation seems still to be linear, right? But you see this K1 come from F. That's first order derivative. What is K2? K2 come from here. That seems to be also first order derivative. But this K1 come from there, which means K2, if I plug in K1 into the formula of K2, then plug in the formula of the last formula, there will be a compositional function of F involving another F. Okay, each F is a first order derivative. So this K2 actually is equivalent to calculating second order derivative. So this is a second order method. So the accuracy will be a third order, depending on the interval. So if you take an interval which is 0.1, first order method, the error will be 0.01 because it's 0.1 squared. For third order method, the accuracy will be 0.001. Okay, so it will be increased by 1 order. It's a modified Euler method. Okay, so next, you may want to generalize the modified Euler method. So the modified Euler method take the first slope at the beginning and the second slope at ending point. You may say, okay, how about the second slope? I'm not taking that one at ending point. I take something in between. How do I know the ending point will be better? You can introduce a parameter to decide where to take the second slope, which is alpha. So if alpha equals 1, this one is exactly modified Euler method, right? If alpha equals 0.5. What does that mean? K1 is still at the starting point, T0, but K2 take something at the middle point, something here. Okay. I don't know, this one would be better than modified Euler. Just give you some flexibility, depending on which slope is more reliable, okay, to help you better predict the true slope, which is K. So this is Runge-Kutta method. So you can also call modified Euler as a special type of a second order Runge-Kutta method. By second order, it is another second order method. Last one for the fourth order Runge-Kutta method, it just based on fourth order, you know, it is basically equivalent to a Taylor series expansion up to the fourth order derivative. It need to estimate the full slopes at different locations, then average those slopes to give you a better prediction of that the true slope K. The truncation error will be a fifth. So here I give you the one strategy for one conventional strategy for Runge-Kutta fourth order method. So you know you need to calculate the K1 is same as the Euler method, okay, and the K2 is similar to the second order Runge-Kutta method with alpha equals half. So if you only just finish the first line, you actually is equivalent to a Runge-Kutta second order method, but then you need to do the second line to calculate K3 and K4. K3, you utilize K2 here, right? And K4 will be utilizing, you just do that. Finally, you give them different ways. I don't draw those tangent line on that figure because that would be too busy. But on Wikipedia, there's a very good figure to illustrate what happened. So you see K1 is at the beginning. Using K1, you can get the point, which is you can calculate K2. And at the middle point, you also calculate K3. Then finally, you calculate K4. Okay, so to approximate the true slope from the beginning point until the ending point, you calculate the slope of this line. You're going to average those four slopes using their weights. So that's fourth order Runge-Kutta method. Any question? All right, so next we want to just pick one method to solve the dynamic of power system and to study transient stability. So here I give the example of simulating the two-area system, the full generator two-area system. So if I choose modified Euler method with the time step 1 millisecond, okay, I know the system is stable because for this plot, I'm simulating the frequencies of full generator. So they are all stay very close around 60 Hertz. So assessment based on this figure will be a transient, will have transient stability. And next, I can increase the time step by 33 times. So now the time step is 0.033 seconds. You almost cannot see any difference between the first and second plot. The third one, I further increase the time step by 1 millisecond, right? Because 0.034, and the system become unstable or insecure because I see the frequency largely go to 64 or 62 Hertz. Okay, so here's a question. So one is use the numerical method to solve the dynamic system for transient stability. If I don't use a small enough time step, the simulation may tell a different phenomenon from the true dynamic of the system. So for this system, I know it will be stable, but if I use very large time step, the system will turn out to be unstable. So this is caused by numerical instability, not transient instability. So which means the instability happens on the simulated system because of the too large time step. It's not really caused by the instability of the system itself. This problem may happen especially with explicit integration methods. The implicit method may be better, usually will be much better than explicit method. Numerical stability is closely related to the stiffness of the system of differential equation. The stiffness is usually defined as a ratio of the largest eigenvalue to the smallest eigenvalue. Or equivalently, it can be the largest time constant to the smallest time constant. It can be evaluated using the linearized model. Okay, so just think about one example. If I have a system which has only just one eigenvalue, or all eigenvalues stay pretty close. To simulate this system, you only just need to know the period characterized by the eigenvalue. Okay, if the eigenvalue has frequency maybe 1 Hertz, the period is 1 second, which means as long as your time step is lower than ½ second, you have hope to track this periodic waveform, right? So you're pretty clear. So for such system, the stiffness is just 1. It's not bad at all. You can know exactly how to simulate the system. But if the largest eigenvalue, the ratio of the largest eigenvalue to a smallest eigenvalue, if that one is stiffness 1000. So what does this one mean? The largest period is 1000 times of the smallest period. In order to capture the largest period, your simulation period need to be long enough, right? You have to simulate a curve of swing for the slowest oscillation. But because they also have very fast dynamic taught by the smallest time constant, your time step need to be small enough to track the fastest dynamic. So on one hand, you have very large simulation period. On the other hand, you have to take a very small step. That gives you some challenge to simulate. So that's why this one can be evaluated based on stiffness of the system. Stiffness increases as more details of the power system, such as smaller time constant, to be modeled or incorporated into the equations. Explicit integration methods have limited numerical stability. For stiff system, the solution may diverge or blow up, and unless a very small step size is utilized. Even after the fast mode decay, the small time steps still need to be utilized to maintain the numerical stability. So if I have a very stiff system, that ratio, the lambda max to the lambda mean to be very large, you need to use a very small time step and finish the simulation for long enough time. The last plot shows the performance of a trapezoidal rule method. So we are going to talk about in a few minutes. That one you see can take a very large time step, but they give you about the same result as the modified Euler method with very small time step. So implicit method has less numerical stability issues. Let's compare explicit methods versus implicit methods. So if we focus on the numerical stability with the fastest dynamics, which is characterized by the largest eigenvalue, okay? So to describe that dynamic, the system variable will change just proportional to the state vector, state variable, and the ratio will be the fastest dynamics. So if we want to simulate this system using a forward Euler method, which is explicit method, we know we're going to use this formula to calculate from one step to the next step. Okay, so we just plug in this one to approximate the original differential equation. And after some simplification. So this one tell how the state variable change after one time step. So we can easily prove if we know the initial state and we know the fast state dynamic. So the state variable will be an exponential function of k. The k will tell how many steps you have simulate for the system. If we want make Sk to be stable, bounded, which means that the method is numerically stable, we hope this ratio has magnitude less than 1. If this one is larger than 1, so when k is large enough, so the Sk will be an exponential function, will blow up, and the system will become numerically unstable. So we have to solve this inequality. So we take the absolute sign, so which means this one either less than 1 or bigger than -1. Okay, and you solve this one. And here we can also assume the system itself is stable. So we don't want the stability of system to be messed up with the numerical stability. Let's just assume that lambda will have negative real part. So we'll be on the left-hand side of imaginary axis. So which means this one, this as a complex number, that will be on left-hand side. So we can easily prove so this inequality has to be true. So the time step need to be less than 2 divided by the absolute value of the lambda max. So if h is less than this limit, the simulation is numerically stable. For the backward Euler method, it will be based on this formula. So we follow the similar process. We can get a formula to predict the Sk from the previous state. Okay, then starting from initial state, we'll have also exponential function. But now you see the lambda and h appear in the denominator, not numerator. So that changed the numerical stability. We want to make everything in this parentheses to have the magnitude less than 1. We only just need to make this one to be stay within that circle, okay? And here, we know if lambda, it has a negative real part, and we can always prove this one will have magnitude less than 1. Because this denominator describes the distance from any this complex number to the distance of 1. This one is always larger than 1. So which means 1 minus h lambda maximum. This one will be always bigger than 1, right? Because if it stay on the left-hand side, and this distance is 1. So if this is bigger than 1, this factor will have denominator bigger than 1. So this factor will be less than 1. So no matter how many k's and you simulate, Sk will be always bounded if the system itself is stable. So we only just need this lambda to have a negative real part. So if the system is stable, the implicit method will be numerically stable. But for explicit method, even the system is stable, the time step still need to be small enough for numerical stability. So to conclude, for implicit method, where you can take any large time step to simulate, as long as the system itself is stable. This is the definition of what is called A-stability. But for explicit method, h need to be small enough to make sure your result to be stable, numerically stable. Okay. Next, let's quickly talk about this trapezoidal rule method. we still want to simulate this system. Trapezoidal rule method is another useful implicit method. It uses a interpolation function to approximate the integral. What that means, for instance, we want the f is a nonlinear function. So if we draw the f versus time, this curve gives you the first order derivative change following this nonlinear curve. So to calculate from initial state to the next state, I need to integrate everything under this curve. So if I integrate, you calculate the total area under this curve, and that one will tell me how much the state variable will change. So to calculate sk plus 1, it will be sk plus everything under that curve. Okay, but if I can approximate the area under the curve by this trapezoid shape, which is ABCD, the only thing missing will be this small area. This one is not considered, but because this is very small, the trapezoid can very well approximate the total area under the curve. So this will be the formula for trapezoid rule method. So it's very similar to modified Euler method. The only thing different is this one will be from the state value to be calculated instead of from previous step. So if you compare, if you visualize that process on that figure, so you have a first line, you have one line calculated at the starting point, and another slope at ending point, and you calculate average, which will give you a good estimate of the true slope. If you compare to modified Euler method, so instead of using the state value calculated from the forward Euler, you are going to use the true value. And compared to the backward Euler method, it's use the average of the two slopes instead of only use the slope at ending point. Okay, so if you compare the trapezoid rule method to the backward Euler method, the backward Euler method uses rectangular area to approximate the area under the curve, but trapezoid rule method calculate that trapezoid shape. The stiffness of the system being analyzed affect the accuracy but not numerical stability. Okay, it does introduce some error, which is for example, this error will be missed. But you can always follow the true curve, even if you take a very large time step. And what is missing will be some fast dynamic in the middle. For example, if this curve is not that smooth, it will have suddenly increased value. So this part will be missed. And this point indicate the fastest dynamic over this time window. But using the trapezoid rule method or backward Euler method, you would not be able to know this fast dynamic. So what happens is, if the system has the true trajectory will be like this one, and the sudden change will be held by the fast dynamic. But if you use trapezoid rule method, it will follow the curve. But it won't become unstable numerically. It may miss some fast dynamic. Okay. All right. Let me stop here so we can. Oh, yeah. We can talk about that course project.